All right, let's just jump right in. That title alone? Entropy can decrease? That's a huge claim. It basically throws a wrench into one of the biggest, most fundamental laws of physics we have. The idea that everything is supposed to decay? Well, maybe that's not the whole story.
So, is the universe just doomed? Is everything just headed for total disorder and decay? It's a massive question, right? People have been debating this for ages. Are we just riding this thing out until it all ends in a cold, dark, quiet nothingness? For a long time, the answer from science has been a pretty grim, yup. But what if that's not quite right? Today, we're going to look at a really interesting idea that pushes back on that.
And this is the big rule that's at the heart of it all. You've probably heard of it, the second law of thermodynamics. The basic gist is super simple. Things fall apart. Order always turns into disorder. And that disorder has a name, entropy. The law says entropy can only go one way, up.
And you see this play out all the time in everyday life. Think about an ice cube in a glass of warm water. It's a classic example, right? That perfect, ordered little crystal just melts and disappears into a messy, disordered puddle. The energy spreads out. But have you ever seen a puddle of water in a glass just suddenly decide to form a perfect ice cube all by itself? No way! That would be entropy going down, and that's supposed to be a big no-no.
So, okay, if you take that simple rule and you scale it up, way up to the entire universe, you get a really kind of depressing conclusion. It's called the heat death of the universe. It's this future where every star is fizzled out, all the energy is just spread out evenly, and nothing happens. Ever again. It's the ultimate state of maximum disorder, just forever.
Okay, but here's the puzzle. The big contradiction. If everything is supposed to get more disordered, then why doesn't our universe look like that? For the past 13.8 billion years, it seems like it's been doing the total opposite. It's been getting more structured, more complex, not less.
So on the one hand, the law predicts this boring, smooth soup of particles. But on the other hand, you look up through a telescope and what do you see? You see the complete opposite. We've got these incredible, massive, ordered things. Galaxies, stars, planets, and they're still forming. They're still being built out of these big, messy clouds of gas. It just doesn't seem to fit.
And this isn't just about stars and galaxies either. You can see this kind of spontaneous ordering right here on Earth. Like when cream separates from milk, or when you see those beautiful, perfect crystals suddenly form in a liquid. In all these cases, something messy is becoming something orderly, all by itself. It really seems to fly in the face of the law, doesn't it?
So what gives? Is one of the most important laws of physics just wrong? Well, the idea we're digging into today says no. The law isn't wrong, but maybe our understanding of it is. The whole paradox, it turns out, might just be a big mix-up. It all comes down to the fact that we've been confusing two totally different definitions of what entropy even is.
Okay, so first up, you've got the old-school definition, thermodynamic entropy. This one's all about heat and temperature. Think steam engines. It was originally about figuring out how efficiently you could get work out of heat. It's a big-picture view, just looking at how energy is spread around in a system.
But then there's the other one, the one most of us think of when we hear the word entropy. That's statistical entropy. This is the one that's all about disorder. It zooms way in to the microscopic level, and it basically asks, how many different ways can you arrange all the tiny little atoms and molecules in a system? The more ways you can shuffle them around, the higher the entropy.
See? Two completely different ideas. One's about energy distribution, the other's about how many ways you can arrange the parts. And they both have their own little problems. The thermodynamic one kind of assumes energy always flows downhill, from hot to cold, which isn't always the case, especially with gravity. And the statistical one gets a little fuzzy about what a microstate even is. But the absolute key takeaway here is that they are not the same thing, and treating them like they are, well, that's where the whole paradox comes from.
So here's the real game changer. It all comes down to what forces are in charge. When you have repulsive forces, think of hot gas molecules bouncing off each other and pushing apart, the system spreads out. It gets messier, and that's when statistical entropy goes up. But when you have attractive forces in charge, like gravity pulling a giant cloud of gas together to form a star, the system clumps together. It gets more ordered. And in that case, statistical entropy actually goes down.
Okay, so this whole idea that it depends on the forces leads us to a new, bigger concept, a more fundamental law, you could say. It's called the restoration principle.
Now, this principle flips the script. Instead of everything being about disorder, it's all about balance. The basic idea is that every single system in the universe is always trying to get to a state where its energy is balanced and stable. So it's not a one-way street to decay. It's more like a constant, universal push towards equilibrium.
So how does this actually work? Well, it's pretty straightforward. First, something happens that messes up a system's energy balance. Then, whatever force is strongest in that situation, whether it's pulling things together or pushing them apart, it takes over. That force then redistributes the energy around, shifting it between potential, kinetic, and radiative forms, until, bam, a new, stable balance is reached.
And what's so cool about this is that this one simple idea explains both sides of the story. You've got a high-energy system, repulsive forces win, particles spread out, and we see what looks like entropy going up. But in a low-energy system, where gravity is the boss, attractive forces win, particles clump together, and we see what looks like entropy going down. It all fits.
This is what makes the restoration principle so powerful. It brings everything under one roof. It can explain the classic stuff, like ice melting. But it can also explain the tricky stuff, like crystals forming or stars being born. And get this, it can even explain things that go back and forth, like a pendulum or a chemical reaction reaching equilibrium. The traditional second law just doesn't really have a good explanation for those.
So the big takeaway here is really a huge shift in how we look at the universe. Maybe it isn't on a one-way trip to a cold dead end. Maybe, just maybe, the real rule is something way more dynamic, more interesting. A constant, never-ending process of seeking and restoring balance.
And that leaves us with a really powerful final thought to chew on. What if the arrow of time isn't just a straight shot into darkness and decay? What if it's more like a complex dance, a constant push and pull of forces, always looking for balance? That would mean we live in a universe that isn't just dying, but is constantly creating, organizing, and rebalancing itself. And that, well, that's a whole different story about where we're all headed, isn't it?